Here we would like to talk about the contribution to the internal energy of a triatomic gas. First, let me explain by touching a point what is degree of freedom is. Degree of freedom is the total number of, in principle, the meaning of that is the total number of independent modes, independent ways in which molecule can move. Basing on this motion, they get energy. As I told you, there are three different kinds of motions. They are like, I will take that, I will explain that by taking an example. Triatomic gas is something like N2O or CO2 or something. It is, say, let's assume that two molecules are along a line. Third molecule is somewhere. It's some simple example of a simple structure of a triatomic gas molecule. It need not be this way, it could be any way. So, what are the possible motions this molecule can have? These molecules can definitely have translatory motion. Each of these gas molecule can move along x-axis, y-axis and z-axis. As they are free to move along each of these axes, each of this one is called a degree of freedom. So due to the translatory motion, it has 3 degrees of freedom, a triatomic gas molecule. And they can rotate also. How do they can rotate? They can rotate about x-axis. Say this is x-axis. So though two molecules are on x-axis, there is third molecule at a certain distance. So it definitely has some moment of inertia and it has rotational kinetic energy. So rotatory motion can be along x-axis. There they possess energy called rotational kinetic energy. Here they possess translatory kinetic energy along x-axis, y-axis, z-axis. Here they possess rotational kinetic energy half I omega square along x-axis. Say they are moving along, let they are rotating about y-axis. When you say y-axis, maybe one molecule is on the axis, but the other two molecules are at a certain distance. So they definitely possess rotational kinetic energy along y-axis also. Even if I consider a z-axis, even if I consider a z-axis, the other two molecules are at a certain distance, even in a perpendicular plane. Thus, there is rotational motion along z-axis also. So they have rotational kinetic energy along x-axis, y-axis and z-axis. That means this is 1 degree of freedom, this is 1 degree of freedom, this is 1 degree of freedom. Altogether, due to rotational motion also, it has 3 degrees of freedom, right? No vibrational motion or vibrational kinetic energy is considered because, as I told you earlier, it is considered only at a high temperature. Only this energy comes into consideration, but now we are not handling that high temperatures in general case. So what we can say is in total, what we can say in total, there are how many ways in which this molecule can move freely independently are 3 and 3. There is 6 degrees of freedom for a triatomic gas molecule. Now, as per a law called as per law of equipartition energy distribution, each degree of freedom has an energy half of RT per gram, or if we are saying per mole, it will become half of KT per mole, whatever, both are same, just different representations. That implies each of these degrees of freedom contributes internal energy to a triatomic gas molecule. That implies total internal energy of that triatomic gas molecule is 6 times of half of RT, or 6 by 2 times of RT. But we know, as per the definition of CV, I can write CV as 1 by N into du by dt, because volume is constant. In the place of dq, we need to write du plus dw, dw equal to pdv. As volume is constant in the case of dv, pdv equal to 0. So no dw, entire dq is du only. And for 1 mole, I can write du as cv dt. So substituting this value here, I will get. So we are now proceeding further, trying to find the value of du. So in the place of this, what we have written du, I can write as, I can write cp dt, cv dt, dt equal to 6 by 2 times of r. In terms of change in temperature, dt's can be cancelled. So cv equal to 6 by 2 times of r, or 3r. We know cp minus cv equal to r, cp equal to cv plus r. cv we have found as 6 by 2 times of r and another r. That is 8 by 2 times of r, that is 4r. As we know, gamma ratio of specific heats is Cp by Cv. Cp is 8 by 2 times of r. Cv is 6 by 2 times of r. That is 8 by 6. That is 4 by 3. That is 1.33 for a triatomic gas molecule. Thus, we are able to find out the value of gamma using this explanation about in terms of degree of freedom, law of equipartition energy, and understanding how do we get that degrees of freedom and how do they contribute to the internal energy of the system. Now I want to just go a step further and discuss the other aspects of it. What are the other aspects that I am talking about? Say for example, if I want to say what is du by dq, du is ncv dt as per definition. dq is ncp dt. dt's can cancel and cancel. Cp by cv is 1 by gamma. So how much is that 1 by gamma? 3 by 4, or 0.75, or 75%. What do you mean by du by dq is 75%? Is out of 100% of the heat supplied to the system, out of 100% supplied heat for a triatomic gas molecule, what happens is 75% is used as internal energy. We know first law of thermodynamics, dq equal to du plus dw. You supply 100%, out of which a major chunk of 75% is gone for internal energy. So how much of external work that is able to do? 100% minus 75%. That's only 25%. So a lot of energy that we have supplied in the case of a triatomic gas molecule is used to do internal energy contribution, and only a small amount of that heat is able to do some kind of external work. This kind of percentages I have discussed for a dry monoatomic and diatomic gas molecules. Please make a list out of that and you can understand that one thing, that in the case of monoatomic gas, contribution of the heat for external work done is the most, and for a triatomic gas, external work done is least, right? That's what's the point that I would like to tell you here in this video. Thank you for watching.